Okay, good. So we are now recording. Okay. So I'm going to share the screen and go back to our Jupyter notebook. Okay. All right, so here we are. So we're gonna run this one, but that's kind of what we've been discussing. Okay. So the classic XOR problem, right? And I'll just kind of summarize really quickly where what we've done and up until what point we were in. So let's just run commands. Okay. So import TensorFlow. All right, there we go. And we can also load the other libraries. Okay. Okay, we have some seeds there. Okay. Then I already discussed this, so I'm not going to repeat it again, except to say, what's the motivation? We're doing the XOR problem, which means there is no linear classifier that will solve this neural network, right? So, or this problem and achieve high accuracy, right? It's not possible. All right, so we generate the data, right? So we generate the data of ones and, from the, numbers between -1 and +1. Okay. So we generate the data, generated y's, all ones first. Then in the previous video, in the last class, we discussed how to make assign the labels, right? So we assign by doing this multiplication here. So we discussed that before. Print out the y's. You can see now this has been labeled correctly. So we discussed that previously. And then you should always print out the shapes. So that's really important, right? So we have, again, this X and Y has how many features? 2, right? And how many samples? 200, right? And then we have 200 labels, right? Which are either 0 or 1, okay? So then we went ahead. We also discussed how this works. We plotted the data, as you can see here. Data is now plotted, and you can basically see that there is no straight line that we can do. So that basically means that if you use just a linear model, it wouldn't work, right? So we have to instead use a non-linear, something that can allow us to create other shapes beyond straight lines, right? And that's where neural networks come in. And then we also split the data into train and test, as you can see. And this is, so we are ready now to do the rest of this. So we're going to be building our neural networks to try to solve this problem. All right, so the first thing I'm going to do is I'm going to try to solve this with a linear classifier. Okay, so I'm going to use a linear classifier and prove to you that I can. All right, so, or actually it'll give me an accuracy, but it's not the greatest accuracy. It's okay, but there are errors, as we illustrated in the previous discussions, right? So that's the issue. So that's what we want to prove today. So I'm going to go ahead, and the first one I'm going to implement. Now, what are we doing? Are we doing regression or classification for this problem? Classification, right? It's classification. We're predicting classes, either 0 or a 1. So then, we can use the very basic neural network that does classification, which is called logistic regression. So at some point when we start looking at the foundations, we will lay, how it works. That's why I'll start a perceptron, then linear regression, then build on top of that logistic regression and so on. But this is a classifier. It's a good classifier. It's not bad. But when the data is not linearly separable, which means you can't draw that line, it has its limits, right? And this is where neural nets come in. So let's go ahead and build this one. So I'm going to do now, make the cell markdown. This is going to be a logistic regression. Okay, so logistic regression is the algorithm in question. It'll basically try to build a classifier that's a straight line, as I had drawn this before. And I don't know if this will annotate. Annotate allows me, I think, to draw on here. So let me see if that works. But what I'm trying to say is this classifier, try to build straight line. Do you see that? So this will give errors, right? You know, that's what we're trying to do. So it's not going to work. Make sense? That's logistic regression. Okay. So how, you know, like this one, right? This is probably the better one. No, that's not the better one. No, what would be a good line? A good separation line here. A good one. Probably. Oh no, that's not good. It's difficult, right? So this one maybe would probably be the best fit line, I would think, because it gets, oh, I got one yellow wrong. Okay, hold on. So you see, this is exactly what the machine learning algorithm is doing. It should then do that, sort of, right? So all yellow are correctly classified, but look at how many greens are misclassified. Do you understand? So this straight line that we're drawing is what logistic regression is drawing, okay? Because that's all it can do. It's like we create an architecture or a mechanism that creates these straight lines. And the only power it has is to create lines and then flip them around or something. Okay, but that's it. Okay, so I'm going to go ahead and erase this. And then how do you stop annotating? Can you just do that? Yeah, I think I just do. All right, so now let's then build that network. Okay, and the intuition is we're going to build the network. We're going to draw it up. Well, I guess we're going to draw it on the whiteboard, and we are going to also define it in TensorFlow over here. So since we're using Keras, it should be pretty straightforward. Let's add a little comment here that just says there are no hidden layers in this neural network. So no hidden layers, okay? No hidden layers. So now let's go here. I'm going to create a model. It's always good practice to do it like this. You know, basically create model and then link everything to it so that you can export the model once it's trained to your application. All right, so what do? tf.keras.sequential, right? So if you remember, we had seen this before. So tf.keras.sequential. This is the thing that will allow us to link all the layers, the inputs, the outputs, and all the hidden layers. Then we're going to do what? Model.add, yeah? And then if you notice, oops, sorry, not curly brackets, but should be this one. And then we take this approach, and then in here, I'm going to add a layer. Okay, in this case, I'm going to add a tf.keras dot dense layer, right? Oh, and from layers, we're going to grab a dense layer. Make sense? So we grab this layer, and then we can specify the parameters that go in this one as well. Okay. So what parameters do we define? We have to define the number of units, the activation, and the everything, right? So because this is logistic regression, right? You guys will tell me. So we're going to switch over to the whiteboard. And this is where you need to, on the exams, for instance, I will usually either give you the code and ask you for this diagram, or I'll give you the diagram and ask you for this code. Okay, so you need to tell me, since we're doing logistic regression, let's think of the network first. Okay, so what does this network look like? Logistic regression. How many? So let's start with the simplest thing, the input layer, right? Oops, that's probably too there. Nope. Oh, okay. All right, so yeah, the input layer How many neurons in the input layer? 2 for the features. Very good. Okay. Then what else? How many hidden layers? We're doing logistic regression, right? No hidden layers. Okay. It's basically just this. That's it. That's basically all we're doing and nothing else. Do you guys see that? Okay. So then we have no hidden layers. Okay. And we need to have 2 layers here. And then we specify that usually we specify the next layer, right? In this case, this layer would just be the output layer because there are no in-between layers here. And in the future, we will see that we can have maybe, how many classes do we have for this problem? 2, but they are what? 0 and 1, right? 0 and 1. So when we have multiple classes, we can, you know, if we have 3 classes, we can do this, 3 neurons. But when we have what is called the binary problem, we can actually just have 1 neuron, okay? And that's because we're just gonna, if you look at the problem, the labels were 0, 0, or 1, 1. So it conveniently falls in the scale between 0 and 1. Do you guys see that? And so this pretty much can be, if it's 0, like a very low number, okay, it's 1 class. If it's 1, it's the other one. But it only works for the binary. Now, we talked, so it's going to be a fully connected, right? Oops, terrible connection there. Okay, so it's a fully connected network, which means we have to learn these weights, right? Weight 1, weight 2, and then the bias is here, right? So the bias is basically we added to, once we've computed this, and this just gives us 1 number, then we add the bias in here, okay? But we don't have to actually code that in, all right? So, or draw it in the diagram, rather, okay? Now, we give it, what are the numbers? Like -1, 1, right? So a whole bunch of numbers. As this is, what's it going to give us? It's going to generate values that could be regression values, okay? But we want to constrain this to be within a range. Do you know what I mean? Constrain this within a range. So what's the range? So the range that we want to constrain this to is 0 and 1. So wouldn't it be nice if we conveniently had a function that did? Do we have an activation function that does that, that takes any number and it's just going to always generate something between 0 and 1? Sigmoid, right? Sigmoid, exactly right. So you have to do the activation function sigmoid. Do you guys see that? This is a neural network. You see it? It's got the framework. It's just, it's a linear, you know, it's a linear model, right? And so now we have this. This is the logistic regression constrained. The hidden layers don't really have, we don't have hidden layers. We don't have activation functions. But this is the network that we're going to generate, okay? And this here just takes care of the final output, which is going to be constrained between 0 and 1. Okay, so now let's go ahead and generate this network in the code, okay? And we're going to test the performance and see how it does. So I'm going to move, share the terminal. Okay. So how do we write this? We say that we want units, right? Exactly how we've done before. And the number of units is, you know, always the layer that we're adding. In this case, because there are no hidden layers, it's just equal 1, right? That output layer, okay? But we also need to specify in here, comma, that in the very first layer in Keras, we conveniently specify the input shape, right? So the input underscore shape equal will be 2, right? So 2. And we just do it this way in case we had like multi-dimensional images, right? So basically that 2 just means that we have 2 features. And then we add the little comma. Do you guys see that? Any questions? All right. And then now we add the activation function, right? Which we have to specify for this layer, which is technically the output layer, we're going to say activation equal signaling. All right. And that should be it as far as that neural network. So now we can go ahead and run this. Basically, this creates the architecture that I drew. Okay. So let's save this code, run it. Okay, no errors. So now we can go ahead and print out the statistics of it just so that we can take a look at it. So to do that, we're going to do model. This is for Keras, model.summary, like that. When we do model.summary and then we're going to analyze it, it gives you the specs of the neural network that we're building, right? So in this case, it says that the output shape, it says that it's a dense layer. The output shape is 1. There are 3 parameters. What are the parameters? W1, W2, and the bias. Okay, that's what that means. The things that we have to learn. Okay, trainable parameters are 3. The none just implies that it can take batches of data. We can either give it 1 input, right, or 5 inputs at the same time. It works right like that. Got it? And this is the summary of your network. So whenever you build an architecture, this is really handy because as you start to build networks that are pretty deep and with a lot of neurons, the number of trainable parameters explodes. I don't know if you've heard something like that the advanced large language models have like 2.5 million parameters, or this is literally how they measure them, by the millions of parameters that they have to train and learn. And believe it or not, by training those, it works. Okay, so now that this is done, we're going to go ahead and compile it. All right, so we have our model. Now we're going to, and then, as I said, next week, we're going to start to specify. Basically, the goal will be to specify, okay, what is this? What is that? In the theory, but a lot of the time, you just call the built-in TensorFlow functions. All right, so now we're going to go ahead and do model compile, model.compile. Okay. Open parentheses, close parentheses. And we're going to specify a few things, right? So we specify the optimizer, which usually for the optimizer, we just have 2 options. So we're going to say tf keras dot optimizers dot, in this case, SGD, which stands for stochastic gradient descent. All right, so that's the stochastic gradient descent algorithm. It's one of the things that we're going to discuss in the theory, how that works, kind of the intuition behind it. Okay. The other option for this one is the atom optimizer, which is still stochastic gradient descent, but supposed to be a little bit better, right? So it's supposed to be a little bit more, it usually works better. They've done some improvements. All right, then we're going to specify the loss function. This is another thing. Remember, in machine learning, there's always 2 functions. The inference function, which is specified by the architecture of the neural network, and something called the loss function, which we're going to talk about. For this class, we'll basically just focus on 2 loss functions, the MSE and the cross entropy. So we will get to those as well. All right, but for now, we're just specifying it. Notice here, we just say tf dot keras dot losses dot binary cross entropy. Binary cross entropy. So I have to explain this, of course, later, a little later. All right, so now we do comma. Okay, and the other parameter that we specify is metrics that we want to use. So, these are the different metrics that we want to specify. You can provide a list of them here by doing square brackets like this. So in this case, I'm just going to use tf.keras.metrics .binary accuracy. Okay, and it'll just print it What's great about this is it just prints it automatically as an output. Okay, and so it's convenient in that sense. All right, so we have the TF Keras metrics binary accuracy. All right, that's all the parameters. So now we compile the model. Okay, so go ahead, and it's thinking. Ooh, error. E, lowercase e, one word. There we go. Any questions? All right, so we have the model specified those parameters. As I said, don't worry if you don't know what those things mean. They're really important, but we have to spend some time to really understand them. Okay. So now we go in and basically go ahead and do the training and the testing all in one shot. Obviously, you could write this code on your own from scratch, but you know, the whole point of Keras is to make things easy for you. So you kind of plug in everything in there. All right, so now we're going to say model.fit, just like that. Okay, we're going to do the same approach here, right? And now we're going to provide the data that we want. So, you know, the first one is to train, so X train, right? That's already provided. Then we provide Y train. So Y train. Then here we can provide the validation set. So it also, so what's happening is during training, it's only learning from X train and Y train. It's not actually learning from the validation set, but it is applying whatever inference function it has learned so far to the validation set. And it's important because for generalization purposes, if it's providing an accuracy for the train set, data that it has seen before, you know, you can expect that it's going to be pretty good at that because it's seen that data before. But when you apply it to the validation set, it never saw that data. And so the accuracy usually goes down a little bit. Does that make sense? So that represents the case where you built a model, you deployed it, and then 6 months from now, something happens, an input, and it just doesn't quite, it's never seen it before. So what's it going to do? Okay, so you'll see in general, the performance should go down. So this is validation data. And so that's going to be X test and Y test. X test and Y test, just like that, comma. And then we can specify the number of epochs. So remember the definition of epochs, that's the number of times that you're going to give it the entire data set. So the number of every epoch, grab the entire data set and you give it. Preferably shuffled every time. So that would be a good approach. So you take one epoch, give it the data set in one order, then the second epoch, randomize it, you know, model fit either has a parameter for shuffling or which is set by default, or you can set it. So I would guess it's probably set by default to shuffle. All right, so that's, I'm going to set the epochs at 200, right? So, you know, this data set is not that big, so it doesn't need that many. Batch size. Batch size. So what is batch size? How many samples do we have, first of all? Huh? But in the train set, we have 100, right? So think about that. And then what is batch size? Why do we need a batch size, or why do we want a batch size? Huh? To make it faster. What's a batch size? Why do we need a batch size? I'm going to say 8, by the way. What's a batch size? Why do you think we have that? Less intensive how? Huh? On resources, right. So here we only have 100 training samples, but what if we had 3 million? Would you give 3 million samples to your computer at once and have it perform all these matrix multiplications? What do you think will happen to your RAM or your computer? It'll fail, right? So the reason why batch size was created is that deep neural networks require lots of data to learn. But at the same time, we cannot give it all the data at once. So this was like, from the start, this was one of the key things that needed to be designed in. Because it used to be, before these frameworks, that you were kind of stuck having to give all the data at once, and it wasn't clear how to, and now you just give it batches. Okay. So usually it's a good idea to make multiples of 8, and the batches don't need to be that big. Okay. So I actually always do like up to 64 and not more than that. Because the thing is, this network is pretty small, but some networks are pretty big. Okay. Okay. All right. So batch size of 8, and you can change that to other values. And then there's the parameter verbose that just means that it's going to print out. So we set it to true basically, so that it gives us information. If you don't want to see output data, then you set it to false. Got it? Everyone with me? So now let's go ahead and we're going to train basically, right? So I'm going to save here. I'm going to move this thing over here maybe. All right. So now, all right. So let's do run. You see that? Epoch 1 of 200, and there it goes. Like magic. All right, so you can see you have to learn how to interpret this. Okay, very important. The loss is printing out the losses is always recommended, always, because like if the losses are not changing, it tells you that your network is not learning. There may be something wrong with it. Okay, so you want to take a look at that. So notice I did 200 epochs. This 13 we had talked about it, right? Someone had asked me this question. Is 13 times 8 equal to 100 or no? What is that 13? Huh? 104. Oh, is 13 times 8 equals 104. That makes sense because the last batch is actually not of 8, right? So because you see that? There's 100 samples. So, well, 12 times 8 is what, like 90 something, and then whatever's left would be the last batch. Got it? Yeah, there you go. All right, perfect. So now let's interpret what we see. So what you should expect is that at the beginning, the performance is going to be low because the weights of this model are kind of randomized initially, right? So they're just random weights. You run the model, it predicts something, it's not very good. But over time, the model is learning. So the weights are improving and the performance should go up. So let's look at the very first epoch. Now remember, every epoch means you gave it all 100 samples in batches of 8. So it's almost like epoch 1, 13 iterations, epoch 2, 13 iterations, epoch 3, 13 iterations, okay? And so it gives you the time it took. It gives you the loss function. This is the thing that we are trying to minimize. Okay, guys, we need to talk about loss and how that works. We'll talk about it, but it's basically the model is taking the predicted and compares it to the real, takes the difference between that, right? And it computes a value. This value over time should go down. The accuracy, on the other hand, should go up. So you can see the accuracy for the first epoch was 46%. That's not very good considering that this is a binary problem and you could build a classifier with just a coin. So if you built a classifier and by flipping a coin, you have a 50% probability, right, of getting one class or the other. So it should at least be, for a 2-class problem, higher than 50. Okay? So then if we look at the validation, it actually it is 81 and the classifier is 48. You can see that it's a little bit better on the train than on the test. Any questions about this part? Nope. All right. Now we follow along. So look at the loss. It starts, it's 80, it starts to go at 79, 76, 75, 73, 71, 70, 69. Loss is 68. So you can see the loss all the way to epoch 200 got down to 68. You see it went down. Now, if we look at the accuracy, let's look at the accuracy of the model. 46, so it goes up 46, 40, okay, 47, 54, We're already up to 106 epoch, and it's 56, 52. See, we got to binary accuracy of 51 on the train set. If we look at it on the test set, it's 58. It's really trying. It's really trying to learn, but it just can't. Right? Because the data is just not separable, right? It's, you know, that's the problem. The data, look, you can't, I draw the lines and you just, every line, every straight line that you draw through this, still you have a lot of errors. Okay, got it? Any questions on that? Okay, so we looked at the performance. Okay, and yeah, we arrive at a, and usually now it, even though this is printing the accuracy for both, so this is printing the accuracy for, where did I have it? Printing the accuracy for both the validation, for the binary accuracy and the, where's the, oh, here it is. So this is for the test set and this is for the train set, right? So you can see it's actually doing a little bit better for the test set, which is strange. It's odd, right? That it does better actually for the train set, but that it's doing that. Okay, you usually want, I would recommend that you usually look at the performance on the test set, because that's really ultimately what you want to do. If you just focus on the train set, what can happen is you can build a model that overfits for your training data, but it doesn't generalize to your test set. And you don't want that. You want the opposite. You want a model that generalizes to your test set. So you want to look at the performance in the test set. Okay, like the data set it's never seen. So in our case, we have 100 samples in 100 samples. Now, I generated 200 samples, but I only use half of them also. It kind of implies that there's a, you know, there might be a whole group of data that I'm not actually like considering. Okay, so that's that idea. Does this make sense? Any questions so far? All right, so what we want to do now, it might be difficult to visualize the results here. So we want to visualize it in a nicer way. So first, let's print out the information that we have, that what are called the keys in the history object. So if you remember, we did the model fit and return it into this object called history. So what's really great about this object history is that it holds a lot of the results. Okay, so it makes it very easy or very handy to use history to now print out results. So I'm going to go ahead and print out some results here. I'm going to do history dot keys. Okay, so this is just so I know what data I have in there. So I have the losses, the binary accuracies, which is for the train set, the validation losses, which is for the test set, and the validation binary accuracy, which is also for the test set. All right, so what I'm going to do now is I'm going to plot this. Okay, so I'm going to go ahead and do a little plot. Let's do, now what do I want to plot? I want to plot the accuracies first. We want to plot the losses and the accuracies, right? Just so that we can see what we saw here in this data in a more intuitive to humans, right? Display, right? This is visualization. So let's do plt.plot. So we've used matplot. So I think the best way to learn matplot is just to look at examples. So plt plot history, and then we're going to do binary accuracy. So that's the accuracy for the train set, binary accuracy. See that? Then we're going to plot, in contrast to this, the accuracy for the test set. All right, so I'm going to do history. And I'm going to say, since I know the name up here, it's binary accuracy and val binary accuracy. So val binary accuracy, just like that. Okay, and then we're just gonna do plt.show. Okay, let's run that. That, I guess that's what happened. Do you guys see? This is the accuracy. Seems to have gone up and then it dropped, right? Now, which one is which? We don't know. We'd have to go to the thing. So there might be a better way to do this. We gave it train first and test second, I think. So should probably just, if we put a legend and just put them in order, this is train. So remember this is train. And then this is test. Yeah, val. So then here, let's put a legend, plt.legend. And the legend is going to be basically the order. So I'm going to say train, just so it makes it easier to interpret. And then this one is going to be test, like that. And then we're just going to say where we want this to appear. So the upper left-hand corner, the location. So we can say upper left. Okay, let's rerun this one. Okay, a little bit better. So now we know at least train and test. Now test was higher, right, guys? The test accuracies, were they higher? They were. So you can see that the test shows in yellow, and they seem to be higher consistently. And the blues are lower. And those are the train accuracies over time. So let's also define so that you know what is the x-axis. So what's on the x-axis here? What's the x-axis? Anyone? The epochs. That's good. So then we can also specify that so that, you know, like we don't have to think. Right? So we can just print thing. So we can say X label. And then I'm going to say here, you know, you give it some name such as epoch. Okay, so I'm going to go ahead and do that. And now I know that it's the epochs, right? We did 200 epochs, right? Okay. Now we probably also don't know what this one is on the Y axis, so we can also label that one. So I'm going to do plt dot Y label. This one is accuracy, so we don't get confused. Now accuracy should go up. That's our goal, not go down. All right. Again, there we go. So now we have accuracy. What else can we add in here? Title, probably. Right. So I'm going to go ahead and add the title. So that's going to be plt title. Oops. And we're just going to say here, model accuracy, basically. You guys see that? So now let's run it. The other thing is, this is important. You can save these. There's a command that's something like plt.save, and you can say plt.save file name, plt.save DPI. DPI means the number of pixels in the image. When you submit to publications, for instance, they want a DPI of 300 or above. So then you can also do that, and then boom, you've got your figures done, ready for your paper or your whatever, your document. Got it? Does this make sense, guys? So as you can see, this went up, hopefully, right? So now it's kind of odd, actually. It took a while, first of all. It went up, then it dropped. Do you guys see any? I find it a little odd. Let's run it again. Actually, there's no reason why we can't just run it again. So I'm gonna just do this, model summary. I'm gonna compile it again, and I'm gonna fit the model again. Let's let it think for a little while. The accuracies are at 50, 70. So this is a much better accuracy. These are in the 70s, right? So what do you think about that? Does that like worry you that one time we were in the 50s and now we're in the 70s? There's no explanation for that, right? This is machine learning. So recommendation, run this a lot of times, okay? Eventually, if you get a model that in the training gets 70 and the testing gets 70, deploy that one. Yeah. Yeah, there's no like, yeah, that's how it is. It is very experimental. We'll talk about this, as I said, how the inference function and the loss function is a little game of just trying. I always call it like grabbing a marble. Imagine a mountain range, grabbing a marble and just, that's it. That's what you're doing. Eventually, you're looking for that marble to find the lowest valley in that mountain range. Think of that analogy. And you're just randomly flipping that marble. All right, so you saw here, actually, this one is a little bit better, but it's hard to interpret, right? I'm looking at it, I'm like, I'm not, I have to read all this stuff. So instead, I'm just going to go to the graph, which is a little bit more convenient. And oops, so I'm going to do, I don't even have to read them, just do this. And then now, I ran it before anyway, whatever. Let's look at it. This one looks a lot better, correct? Would you agree? It didn't have that crazy dip. This is more the expected. Also, it seems to have learned really fast. You can see that test was lower than train, then it became higher, then it's like, and then test became pretty good. I find it very odd. So actually, I find this as a good example of the fact that linear models generalize really well. Okay? Do you know what I mean by that? So linear models, this is one of the things mathematicians would have told you. Linear models are better because they generalize really well. Whereas the neural nets overfit. Because you're building a curve and the curve is like exactly around the thing. So when you apply that to a test set, that may not be as good. Do you see what I'm saying? Whereas if you just use a line, a straight line, then they say, oh yeah, it's better because it generalized really well because it's just a straight line. It's less specific to the trained data. So that's like a thing, it's a debate that people always have. But anyway, I would say that actually is probably what's happening here.
Test the train model and test the train model again. Is that why it actually changed?
No, it's just random. It didn't. So I think I get your question. You're asking the question like this, I think. Did we train it and have these weights and then we kept those weights and we just added to those weights? No, we like reinitialized the weights. That's a good one because you're thinking in terms of fine-tuning a model where you actually train it a little while, preserve those weights, and then train it a little bit more and use those weights and just add on to them. This is a common practice, actually. But in our example, we're not doing it. Do you see that? We're just resetting the weights. So this is an example of, so to answer this with an example, if we ran this 10 more times, we could see the dip again. We may actually try that because machine learning is kind of like that. But let's just keep analyzing this one. We'll run a few more trials. I mean, that's the whole point of this discussion today. So you can see it's going up. How high did it get? Did we reach 80? Probably not, right? And it kind of settled around, well, actually, for the train set, it's under 70. For the test set, it's roughly at 70, 72, something like that. Do you see that? So that basically means your model has a 72% accuracy on the test set. That's how you should sell it. I have a model that has a 72% accuracy. Okay. Could you do more epochs? Yes. right? That's going to be your homework, just playing with this, right? So you're going to try different network architectures, give it more epochs, etc. So let's run it one more time. I'm going to go over here, logistic regression. Run it, run it, run it, run it, run it. It's training again. Accuracy. See that? 57, 57. See what I'm saying? It dipped again. Oh no. Yeah, right. So here, now a lot of people, what they do is when they run multiple ones, they keep track of them and they save what is called the checkpoint. And so they'll have, let's say that I did 3 runs, right? And I have the metrics saved for the 3 runs that I ran overnight or over a week or whatever. And then I have 3 checkpoints. The checkpoint just means that I save each model, right? And then I look for the accuracy that was the highest. So in this case would have been that second one, right? In the 70s. And I just grab that checkpoint. And that's the one I deploy. You see that? That's how it works. So I think by now it's finished. Yeah, so now, again, I don't want to have to read this, but it seems to have arrived at 68. So it did improve over time. So now let's run it. See, this is different, right? So now here it learned, then it dipped, then it learned, and then the test set again, look. Patients would be very happy with this, right? So this just shows that it's generalizing well. And look at the value, 67. Before we were at 70, right? So it dropped, it wasn't as good. Making sense? All right, so now let's print the other one, the loss. So this was the accuracy. The other metric that is recommended that you print is the loss, right? And then we'll do a couple more. So let's now do the loss. Oh yeah, sorry. Randomly. So it's default. Huh? So can you? Sure. You're starting, 0.70 in the test set, and the train is in 0.60. Why does it stay so flat? Were all of them like that? The other ones were like this. And this one was just pretty stable like that. It's because it's a good question. So it's a combination of initializing the weights randomly and a combination of gradient descent. The gradient descent algorithm, literally, we haven't gotten to that yet, but think of it as a mountain range, right? It starts looking for a valley, the deepest place, and sometimes it starts on that side, sometimes it starts on this side. So it's starting in different places. And so it's going to arrive at different points, locations, and you just pick the lowest one. That's why you do it multiple times. It's very like you have to run them, right? Do the runs and look at the analysis. But that's a good question. We will definitely look at that, okay? To answer your question, I would say it this way. The weights should not be initialized to all zeros, should not be initialized to all ones. Instead, you should initialize them at least to all random, so different weights randomly. Better yet, initialize them randomly, but with a distribution. So like a normal distribution or something. You see that? And so there's various ways, and it is very important how to do that. And like I said, as we start moving into the loss functions, we need to talk about that. That is accomplished through gradient descent, the gradient descent algorithm, which we don't actually have to implement. That's what TensorFlow does for us. So we have to talk about the gradients, the derivatives, that we need to calculate at specific points and all of that, right? So that's an upcoming lecture. All right, so for now, I'm just trying to motivate neural networks. So as you can see, logistic regression has the framework of a neural network, but it's not a neural network because it cannot do the curvy thing, right? It's only doing the straight lines. And that's why we've only been able to achieve about 70%. I don't know, you guys are all running this, I assume. Has anyone achieved something higher than, say, 75% accuracy on the test set or the train set? No? Where are you guys at? So whoever's running this. 70? You're all at 70 basically? Okay, so we need to improve that, right? And so my goal is to prove to you guys that the only way to improve it is through a network, a deep neural network. So the next thing we want to print out is, or plot, is the loss function. So we're going to do that too. plt.plot. So again, this is going to be history. Dot history. Okay. And then we're going to print the loss. So remember, this order is important. So I'm going to print the loss, right? That was the name of it. We can just go back to these names. So we're printing loss and val loss, okay? Because we want to compare these two again. You always want to look at both of them, okay? Very important. So plt dot plot, okay? And then we can do history dot history. And this one is going to be val loss. Val loss. Okay. And then plt.show. So that should get us pretty close. plt.show. This is going to be obviously the loss function for this model. So if we run it, what do you see? Look at the loss. It's very strange. So we don't have the legend, right? So we want to add the legend. So it's easy to interpret. So plt.legend. Going to be, we need to provide this in the same order, right? So list of train and test. Okay, and then we just specify where we want this located. So location is going to be upper right, maybe? Because, yeah, the loss is going down in theory, so we want to do upper right. Okay, run it. Okay, so the train, it starts at 72, it seems, and it goes down. You see that? And the test is kind of very strange behavior. It actually got worse somehow. Because the loss, remember, whereas the accuracy should go up, you're minimizing the loss. So the loss should be going down. Okay? And this is still over epochs. So we can just copy some of these and change them. Just going to copy these. Change it. So label it appropriately. So this is the title should be model loss. Losses, maybe. Epoch is correct. And then the Y label should be the loss. Okay. So now let's run it. Yeah. So now it should be properly labeled. But as you can see, it's not a great thing, right? What you would want is for both of them to be tracking equally and, going down, right? Make sense? All right. So let's run this one more time just to see how it performs. So that's logistic regression. Okay. File. Now let's do the training. Binary accuracy is 47 and 44 initially. Let's see where it ends up. Proving. Did improve. $67 and $72, right? Pretty consistent. The losses, 68. But again, it's nicer if we can just plot it. So let's go ahead and plot them. Okay. And then let's plot the losses. So look at that loss. Let's see if that looks. All right. This looks much better, right? This is kind of what you're looking for in a model. This is a well-behaved model. right? At least in terms of the losses, you know, they're both going down, the losses, okay? And the accuracy actually looks pretty good. It did 50 epochs. That's actually a lot of epochs, right? So it's struggling with this. And it couldn't get any results. Then it found something and it started to go up. But again, it gets at 70%. We can't seem to solve this problem. Do you guys see this? Any questions? Making sense? All right, so basically you've established you're like at a point, so you're basically in the 1980s right now. And in the 1980s, with the computing power that you had, this is what you achieved. I'm serious. This is literally where you are. You're in the 80s, sometime in the 80s. Okay, and then now comes 2012, right? And you've learned new things. And so you need to solve this problem better. So what are we going to do? We're going to now implement a deep neural network. Okay. All right. So let's go ahead and do that. I'm going to do cell, find markdown. Okay. Let's save this one. Okay. Let's call this a deep neural network. So I'm just jumping to deep learning, right? So this is a deep neural network. You know, we're now building, you know, pretty good algorithm. And I should specify also that it has, well, it's deep neural net with, I'm going to make this with 3 hidden layers. You see that? 3 hidden layers. Okay, so I'm going to run. Okay, so usually I want you guys to kind of get into the habit of drawing these out. Okay, so we're going to switch over to the whiteboard. Yeah, switch over to the whiteboard. And we're going to draw this out. So actually, remember, this was the logistic regression, right? We had 2 inputs and 1 output, which had a sigmoid function. Now we are going to build a deep neural network. So let's go ahead and draw it out. Okay, so, okay. So what do I want in this one? Okay, so we're starting at the input layer. How many inputs? How many? 2. Very good. I set 3 hidden layers, correct? So then, three hidden layers, H1, H2, H3. And then after that, what comes? The output layer. Okay, so we've got the output layer. So how many, let's start with the output layer because I think we already knew that one. How many neurons in the output layer? 1. Did it have an activation function? Sigmoid. Sigmoid. So what, so you might ask me, you know, where did you get this 3 hidden layers from? Right? You might want to know that. Did I use some special calculator that tells me? No, it's just, this is why it's called architecture. You're the architect. So you define these architectures, and over time you develop a certain kind of an intuition for which architecture. When you have really large models, you kind of want to do this funnel approach, which basically means that if you have, let's say you have 1,000 inputs, so as you start defining these, they should be smaller to kind of force the model to learn with more. This is going to be your homework assignment. Okay. So I'm just going to do this deep learning. So I've done like a very basic one and a very powerful one. And you're going to do everything in between. Just go nuts. All right. And play, you know, try many architectures and then just see the results. And it should be a really good exercise to show you how this works. Okay. All right. So I selected 3 hidden layers. If I had just selected 1, so if I had just selected 1 hidden layer, 1 input, 1 output, it's not a deep learning neural net. It is just called a multi-layer perceptron. Have you seen the multi-layer perceptron before? You saw it in Weka, right? Weka had that. It had it for a long time. But if you do more layers, that's when it becomes deep learning. That's it. Nothing more. All right, so now I have 3 hidden layers. How many neurons do I want in each layer and why? 8, 4, and 2. Okay. Why did you start at 8, 4, and 2? Where did you get 8 from? But the input here is 2. So by your logic, this should be 1, and then this should be half of 1, and yeah. So it's kind of it's there's no answer to it. That's the point. I can only tell you like rules of thumb or something. I can't really tell you. So what I do usually when I have very few is I kind of give it kind of the same, maybe a little bit more. Like I said, if I had 1,000 inputs, then I definitely funnel it. Okay, why do you funnel it? Because you're forcing the model to learn with less. It's almost like if I give you guys a month to do a homework assignment, you're not going to do it until the night before. Right, exactly. And so so now if I want you to really move, then I'm going to assign it for a couple of days from now, something like that. It's the same idea with neural nets. You're forcing them to learn. Otherwise they're just going to start, who knows what they're doing, elucidating, right? And so you want to basically force them. But because this model only has 2 inputs, we can keep it at a low number, but still give it some capability. So I actually, for this one, picked 4. No reason in particular. Just your homework assignment, try 1,000 on each, see what happens. It's not necessary to have 1,000 probably, but that's going to be it. I just want you to play with it, get a feel for it, build a few. So I'll write something down, but I just want you to play with the parameters and see the results, okay? This model should do okay already, okay? Now, another thing I will tell you guys is actually it has been proven that you can build a network. Like you could build, this has 4, 4, and 4, right? So let me actually go to another one. That one has 4. It has been proven this. See, if I had 4, 4, and 4, I can build this network in theory that had 4, 4, 4, 4, 4, 4, 4, 4, 4, 4, 4, 4. Guys, do you see this? So this now has 12 and then the output. Do you see that? And it's been proven to be equivalent as long as it has all the layers. Sounds shocking, right? But the reason why people don't do it like this is that this is a much bigger matrix multiplication. You see that? So because this is a much larger matrix multiplication, it's like inefficient for the computation. So the other one is smaller matrix multiplications. Okay, got it? And so people do it this way. Okay, so that's kind of the intuition. Any questions about that? All right, so now let's go ahead. So we have this one. It's been defined as having 4, 4, 4. This one has 2, and this one has 1. Are we done? Are we done? They are connect. Well, we will connect. Okay, I see what you're saying. Yeah, we'll create the TF-Keras sequential, and it will connect it. We'll say that they're dense. It's going to be fully connected. Look at this. How many parameters is that going to be? See how it starts to explode? Now, if you put 1,000 neurons on each one of these, that's a lot of parameters. Okay, so you guys will print out these results in your homework, as I said, just to kind of visualize it. But are we missing something? Activation functions, right? So activation functions, it's something that you're going to also, I usually just do this when I write the activations. And in this case, what activation functions do you want to use? So I kind of said, I gave you sigmoid, tangent, and ReLU, right? So again, in your homework assignment, just change the activation function, see the results, but I'm using ReLU. It's just like recommended, experimentally. Okay, so that's basically it. That's your neural network. It's currently defined, and now we can code this in TensorFlow. So let's go ahead and build our deep neural network. Should be convinced that this is a deep neural network. So we're going to go to Jupyter. Okay, and remember this, right? We are trying to beat. So you're in a competition, right? And you guys entered the competition and you achieved 70% accuracy on train and test, basically. And this is your loss. And you're like the winner right now, right? And then comes in a new team, and the new team is like, okay, we're going to do a different architecture. And it's going to be a nonlinear architecture. So we're going to build a model equal tf.keras.sequential. Okay, tf.keras.sequential, and then I'm going to do model.add tf.keras.layers.dense. So remember, dense means it's fully connected. Later on, when we want to try other architectures that are really large, we can add this thing called dropout that just drops connections randomly, depending on how we tell it to do that, but we don't have to worry about that now. Okay, so then let's define each layer. So units for the first hidden layer is going to be 4, right? We also, in that first layer, we can conveniently set up the input shape. So, oops. So input shape, it's going to be, again, 2 neurons, comma. All right, and then the activation is going to be ReLU. Lowercase. ReLU like that. Okay, so that takes care of that first layer. Then we can do the other ones. So model.add tf.keras.layers.dense. Units is going to be what? This is the second layer, so 4. We don't, and then we just add the activation here. Activation equal. Okay, and we're going to add the third hidden layer. Model.add tf.keras.layers.dense. Okay, number of units, once again, 4. This is the third hidden layer. Activation should be ReLU. Okay, and then the final one is the output layer, model.add tf.keras.layers.dense. How many units do we have here? Just 1, right? So units, the last layer, equal 1. And the activation for this one is what? Sigmoid, right? Sigmoid. Later on, as we do multi-class problems, we're going to start using, instead of sigmoid, we're going to use the softmax. And that's just because, of what we described on Tuesday. Got it? That's it. That's, you know, that's a deep neural network. That's it. Right. So now we can go ahead and run it. Okay. So we have it set up. Let's do the summary. This should be interesting. Should be pretty interesting. So I'm going to do model dot summary. See that? We have 4, 4, 4, and 1. Look at how many parameters it has to learn. 57. Do you see that? That's the weights and the bias that we have to learn. Now, let's say that I do 40. 40. Can I do this? Sure. Why not? Let's look at the number of parameters. How many parameters do you have to learn? 3,441. That's what it has to learn, this model. I go over here. I'm going to make this 400. Run it again. How many parameters does the model have to learn? 322,401 weights. It has to learn that. That's a huge neural network. And it's actually not, you know, some of these large language models are, I don't know, like 2.5 billion, I think it is. The parameters, they're huge. One last one, 4,000. That's literally a neural network with 4,000 neurons. That's 4,000 connections, right? 32 million. Do you think your laptop will be able to learn this quickly? So I won't do this, but this, you know, do this for your homework assignment. Okay, just play with these, run them, see the limit, basically, of the size of this. But it should be, you know, an example of this is the number of weights that the neural network has to learn, right? It goes from inputs and then back, and it has to, initially they're randomized, eventually they should have the right values. That's a lot. And also totally unnecessary for what we need to do. So I'll go back to 4. And just these little things that we did, if you notice, the hidden layers, the activation functions, you know, basically 57 parameters that we have to learn, not 32 million, you know, should be enough for our model to do a little bit better, right? Any questions? Yes, exactly. At what point do I switch to GPU? At the point where my laptop is taking too long to finish. Probably. Oh, yeah, absolutely. Way before that. Yeah. This is why I would give the data in batches also, right? I wouldn't give it because that's going to run out of this, the issue of RAM, and there's the issue of the CPU. But exactly right. So like the code I'm writing would run on GPU without doing anything, with no changes. You want to do GPU? So the only, okay, so I have to give you a really large data set as a homework assignment. That's basically it, because then you won't be able to break it without, or solve it without a GPU. All right, we can do that. Sure. What's your question? Go ahead.
I guess, how do you use GPU, and you know, are we going?
Yeah, so like I said, I usually like to do everything on my laptop because, you know, exactly, sit on this couch, you know, whatever. But at some point I'm running something and it's just not taking too long. It's just, and I want to see, and so at that point, then I deploy to GitHub, and then I go to my GPU and download it and then run. As far as the code, especially with Keras, it should be pretty straightforward. It detect, because what it does is it's detecting actually the if you have a GPU. And then usually it says, like we're running this on the Jupyter notebook, but if you ran this on the command line, you would see a little bit more output. And then you would, usually it says, didn't find GPU running with CPU. Make sense? Yeah. And just, we don't have to change the code. That's actually the beauty of this. This is why they invented it this way, is that if you use the CUDA library, for instance, which is what the C library that, you know, allows you to interact with the GPU to do machine learning, you literally have to write code in another way, right? In another way completely. That was too hard for everybody. And so they decided to create something that allows you to write the code in Python in a way that will work both in GPU and CPU with no changes or minor changes, something like use CUDA instead of CPU. You know what I mean? And so, yeah, and so really the choice of using a GPU is only that you have to, it's only when you have a limit, basically, that it's no longer on your laptop able to process. But really, we're talking about image processing, for instance, where the images, you know, are 784, like MNIST, and MNIST actually runs nicely here, but something bigger than that, and a really large neural network like the one I built with, you know, yeah, 400 or whatever. At that point, it'll probably might start to slow down. And so that's the moment when you want to switch to GPU. But as far as running it, it runs exactly the same, just with 10 times as faster probably. So what was taking you roughly, you know, maybe I would say 10 hours could probably take you an hour. But yeah, did I answer your question? Yeah, so that's how it works. So as far as, so for us to get GPU, it's an issue. Huh? Videos. I don't think that we can use so to use GPU, we need a special type of a GPU. The NVIDIA GPUs that are made for both graphics and machine learning. And so I would have to probably get the Scholar GPU cloud for you guys to be able to do runs like that. So I may be able. So if you do need Scholar, like if you want to try the cloud version, let me know. We can get the CPU cloud, which is pretty easy. The GPU cloud is a little bit more of a challenge, but I can probably request. Is
that what tensor cores are?
What?
Tensor cores, so like the new GPUs have tensor cores.
Tensor cores, that's probably a Google thing. Right, and then you have to go to the cloud and then use their cores, but it's fine just to use NVIDIA cores. They're just as powerful.
I wasn't saying it's on NVIDIA cores, but these cores are having different amounts of these different types of cores.
It just may be a very specialized core. They're probably very expensive.
Like the GPU I have has so many tensor cores.
What GPU do you have? Yeah, I have the RTX 2080.
That should also have a different amount of tensor and CUDA cores because they have different tasks, kind of like processor has cores, P cores, efficiency.
I just basically know that I just get a NVIDIA GPU, either a 2080, a 3090, or a 4090, I think. Yeah. Yeah, they're expensive for sure. We do have a GPU cloud. Let me see about getting that, and I'll make it available. If you do need the CPU cloud, I can probably get that more easily. But the GPU cloud, and then I would give you like but for it to make sense, I have to give you like 2 million images or something. You know, something pretty big. Does that make sense? Yeah. All right. But anyway, hopefully I answered your question. Both TensorFlow and PyTorch were designed to process massive amounts of data, not just to build deep learning, but to process massive amounts of data. That's why we always read the data in batches. And to switch from CPU to GPU, we hardly have to change anything. Okay? Got it? All right. Okay. So hopefully that made sense. All right. So let's go back to this. So I'm going to run the deep neural net. Okay. Kind of remember where I was. Oh yeah, so we have 57 weights that we're gonna learn. This is pretty easy for my laptop to do. Okay, we did the summary. Now I'm gonna go ahead and compile it. So same approach, I can do model dot compile. Oops. And again, these three things we have to specify in the theory later in the class, but we're going to use the optimizer, which in this case, was going to say TF Keras dot optimizers dot stochastic gradient descent. I could also change this to atom. I believe it's with an uppercase. It's just a more efficient version of stochastic gradient descent that somebody like really found a way to improve it. But for now, let's just use this one. Stochastic gradient descent is just the algorithm that learns. So now that's like that. Then after optimizer, we're going to specify the loss that we want to use. In this case, we are using TF Keras dot losses. There's only a handful of losses that you will be using anyway, but I'll get to cross entropy for sure. And also the mean squared error, obviously. So TF Keras losses binary cross entropy. Okay. Just comma. And then the metric that I'm using. The metrics equal. We can put several in here, right? So you can also, as part of your homework, look for, more, right? Precision, recall, F measure. Try them out. TF Keras dot metrics dot binary accuracy. And that's with parentheses. Okay, so that's the parameters that we usually define for a model. And this is actually an easy part. It's barely, changes very just slightly. And so it's not such a big deal. Okay, now remember, this is a deep neural network. So, I'm expecting this to do really well. So I'm going to do history. It's going to be equal to model fit, model.fit. Okay. And again, just like before, X train. Going back to that question you asked me about, the GPU, TensorFlow is like, it's either TensorFlow or PyTorch. That's it. There's no this is what the very best use. This is what Google uses to build their stuff, right? And so kind of answer that. There's one more thing, which is called transfer learning. And that's a slightly different thing we'll talk about at the end of the semester, okay? Which is when you download models that are trained by other people and they're really large models. And that's extremely powerful. And we do have a course for that in this program, but it's a grad level course, ITS 530. It's just the applied deep learning is transfer learning. But anyway, so this is definitely state of the art for sure. All right, so it's X train, Y train. Okay. So that's our data. Then we're going to do the validation set, just like before, validation data. And that's going to be X test and Y test. Test. All right, and then finally, how many epochs? Well, we want to compare apples to apples, right? So get into the habit of, because you could give it 400 epochs to the previous model, and maybe it just needed more epochs, right? So you definitely then need to give it the same number of epochs so that you can compare, really. Because you don't know, over time it could do better. But in general, I think for the XOR problem, at least, which is a highly studied problem, Basically, it just canceled. Batch size, I think we were using 8. And then verbose. Equal true. So now we're going to go ahead and just run this, you know, let it fit once again and see if it does well. 69. Validation loss. What's the accuracy? 53. It's not doing well. Doesn't seem to be learning, right? Right? It's actually doing worse than oh, you got 98. Okay, so it did well for you. Not for me. So it finished. And I don't know, how about the rest of you? Where are you guys at? 86 and 82. Okay. What about the rest? Where are you? And you got 98. All right, so you're winning right now. You're gonna get the $1 million prize. So what do you do then? Run it again, right? Run it again. In fact, whenever you do this, when you know, run it overnight multiple times, save your checkpoints, right? And then track the results. If it turns out that in the 7th one, that's where I did the best, grab that checkpoint, go to the competition, win the prize. Okay? Huh? Yeah, you have to write the script to do that. And there's a function to save checkpoint. So that you save each model. You're going to throw away all the other ones, but then that's the one model you're going to use. Got it? So we'll look at that later. All right, so let's just, so mine actually did really bad. So let me copy the other things. So I like to see the graph, right? So let's look at my graph. I'm going to copy this. Copy that. So we know that somebody got 98. All of us then now know that we can achieve 98. So it's just a matter of running it again until we have that one that achieves this. And remember, though, it's not just 98 in the train set. It should be 98 in both the train and the test. That's where we want it to be. And then, as I said, that's the model that you deploy. And the reason for this is, as I said, that the weights are just what they are. What is okay? Pretty odd. Maybe I have a typo in my code, I think. And I'm gonna do this also. It's the loss. So that's very strange looking. Okay, so the losses did go down. But my performance stayed. It's really odd. I think it's just that the yellow line is probably on top of the blue line. All right, so I'm gonna run this again. I need to have something a little better. Run it, run it, run it. Run it, run it. There we go. Ah, much better now. I'm getting 88 and 84. Not as good, but okay, so it's doing this. And you know, another reason why you save the checkpoints, it could turn out that you never get that accurate. You know, you could get unlucky, right? And because it's kind of doing things on its own. So you may have gotten that 98, 90, 98. And then every time you run it again, it's also 88, 88. So if you save that checkpoint for that 98, you have it. and you can always just retrieve it, right? So it's just a convenient. This especially now. This also another thing I should say is this is not a large model. It takes less than a minute to run. But what if it was a really large model that's taking, you know, all these 10 hours? You see, 10 hours, 10 hours, 10 hours, save the checkpoint. Otherwise, you know, it's going to take a long time. Anyway, that's just good practice. All right, so let me look at mine here. Ah, okay, much better. You can see it's definitely above 90. Do you guys see that? Mine is definitely above 90, and the loss function went down. So now at this point, it would be good then. With the graph, I kind of know what it is, but I want to see the specifics of it. That's going to be your homework assignment, printing out precision, recall, F measure, and like do a little summary of the actual scores. Okay? You guys get what I'm saying? Make sense? All right. That's it. So that's basically the hopefully it made, you know, you've seen the power of neural networks. That was the whole idea with the classic XOR. You saw that's a difficult problem to solve with linear models. When you add deep learning, you know, neural networks, then it becomes obviously solvable because literally we were able. So now kind of to conclude, you know, we can, if I go to the annotate section here, I can basically say, you know, intuitively that the neural network did something like this, right? So good. Remember, the neural network is defined as a universal function approximator. It has been proven by people that it can approximate any function, like literally, I guess anything, any function. We don't even know how sometimes, right? But it can approximate any function. And so this is a function that creates this shape. Because you think of it this way, if you get confused, you know you needed this function. You as a human know you can draw this function. The model somehow creates a function that draws this because this is the best accuracy for the objective. Do you guys see that? That's it. All right, so I will stay to write out whatever the assignment is. This will be due a week from today, but as you can see, all I want you to do is try different architectures, okay? You know, try more neurons. We're already at a really high score, but really if you could get 100 on the train set and 100 on the test set, obviously that's a goal and objective. But definitely, I think you should all be at like over 96 on both train and test. So do as many runs as you can. Please provide a few summary statistics. Let me stop this. A few summary statistics at the end. So because as you can see here, you know, although I know where it is, I'm not exactly sure if that's 96, 98. So just print them out, okay? You should be able to figure that out. And then try different architectures and different. All right, I'll just write a list of things for you to try. And then that's it. We're done for today. Next week, we will start to kind of break things down, start with a perceptron linear regression build up, okay? All right, so have a good weekend. And I'll stop the, need to say this.